In this video, I'm going to do an example of how we can use congruent triangles to prove something. Not just prove the congruent triangles, but prove something else. In this example, I'm going to be proving that a construction is in fact constructing what it claims to construct. And then in the next video, we will be using congruent triangles to prove properties of quadrilaterals, such as the kite and the rhombus and so on. First of all, an abbreviation. CPCTC stands for corresponding parts of congruent triangles are congruent. This is kind of the definition of one of the definitions of congruence. Two figures are congruent if all the angles are congruent to all the corresponding angles in the other figure, and all the segments are congruent to the corresponding segments in the other figure. So the way our proofs are generally going to go is we will prove some triangles congruent, then we will use corresponding parts of congruent triangles to get parts congruent, and then we will make our conclusion. I found a page of two-column proof tips on the internet, and we're going to jump over and take a look at this pink sheet. Okay, I'm at the Mrs. E Teaches Math page. It's mrsetteachesmath.com, and she has a number of things that are useful here. But the one that I want to pay attention to here is this one right here, the two-column proof tips. We're going to number the steps. We're going to start with the given information. We should label the diagram with the given information. It needs to be done in a logical manner. The reasons will be postulates, theorems, definitions, or properties. We can use symbols so we don't have to write out all the words. Now, one of the things I'd like to emphasize, and the same thing Mrs. E emphasized here with her stars, is that sometimes we talk about the segments themselves, and sometimes we talk about the lengths of the segments. We use segment AB is congruent to segment AC, or angle A is congruent to angle B, when we talk about segments or angles being congruent to each other. These are the actual geometric objects. Geometric objects can be congruent. However, if we want to take a look at their measurements, this is a little bit different. We use AB equals AC, and the measure of angle A equals the measure of angle B when we talk about only their measures being equal to each other. We need segments and angles in this format to add or subtract them. So if you're going to want to say things are equal, it must be numbers. And AB here is a number. It means the distance from A to B, or the length of segment AB. And this is a number. It's the measure of angle A. Who knows? Maybe it's 32 degrees, for example. When you're doing arithmetic, like adding measures together to get 180, you must be working with the measures and not the angles themselves. To convert between equals and congruent, we use the definition of congruent. If congruent, then equal, or if equal, then congruent. So it's easy to pass from one to the other. Now I'd like to do an example where we look at the construction of the perpendicular through a point on a line and prove that the construction is valid. Here is a little video that shows how to do the construction. I will let you look at that on your own. First of all, we strike an arc on either side of the point C. Then we open up our compass and strike an arc above from the left and strike an arc above from the right. And that gives us our point. And then we can draw in the line. And we want to show that that's perpendicular. So this is our main example for this video. We're going to be using congruent triangles to prove a construction. The construction is to construct a line perpendicular to a line through a point on the line, as we saw in the video. And we want to prove that the construction is valid. The first thing we need to do is make a diagram. Here's the diagram. You're going to need to pause the video so that you can copy the diagram down on your sheet of paper. So what we're going to do now is use this diagram to prove that it is in fact perpendicular. Okay, so let's see what we have congruent. We have this segment CY congruent to this segment CX by construction because this was the same radius. I have this segment up here congruent to this segment here because that was the same radius. And I have this segment congruent to itself. And so let's see how the proof works. First thing we have here is that segment XC is congruent to segment YC by construction. Then we have segment XD congruent to segment YD. That's also by construction. Then we have segment CD is congruent to segment CD. That's reflexive property of congruence. A segment is congruent to itself. This is enough now to prove the triangle's congruent. Triangle XCD is congruent to triangle YCD by side, side, side. So now we would like to make angle 1 and angle 2 90-degree angles so that they're right angles so that we have perpendicular lines. Remember, our goal is to show that they're perpendicular. So angle 1 is congruent to angle 2 by corresponding parts of congruent triangles are congruent. Maybe I should preview the rest of the proof. So our goal is to show perpendicular. In order to show perpendicular, we need right angles. In order to have right angles, we need 90 degrees. So we want to get angle 1 and angle 2 to be 90 degrees. So right now, 1 and 2 are just congruent, but also they're a linear pair. Before we talk about them being a linear pair, I'm now passing to the numbers. Notice that this is an equal sign, and I have the measures of the angles being equal. This is definition of congruence. Angle 1 and angle 2 are supplementary angles. The reason is that angles in a linear pair are supplementary. This means that the measure of angle 1 plus the measure of angle 2 equals 180. That's the definition of supplementary angles. Now I'm going to be substituting. I'm going to be taking out the measure of angle 2 and I'm going to be putting in its place the measure of angle 1. I like to think of substitution like a volleyball game. There's a player that comes out of the game and there's a player that takes their place, but the rest of the volleyball game stays the same. Let's see what we get by substitution. Now we have the measure of angle 1 plus the measure of angle 1 equals 180 degrees. That's substitution using lines 6 and 8. Now we just need to do a little bit of algebra. X plus X is 2X. Measure of angle 1 plus measure of angle 1 is 2 times the measure of angle 1. And then we're going to divide both sides by 2. So the measure of angle 1 is 90, and maybe you can anticipate the rest of the proof now. Since we have a 90-degree angle, angle 1 is a right angle. That's definition of right angle. And since we have a right angle, we're going to have perpendicular lines. And our conclusion is that line CD is perpendicular to line XY by definition of perpendicular lines. I hope you found this first video helpful. In the next video, I'll be using congruent triangles to prove properties of quadrilaterals.